We do have some common growth rates, so I want to go over those in terms of the big O notation. So we first have what's called constant time, or O of 1. Now we just use 1 to say that we have a constant number of steps. We technically, I guess you could say like O of 2, O of 3, but O of 1 is the norm for denoting constant time operations. We have O of log n, so this would be logarithmic time, so the algorithm has a logarithmic number of steps. We have log n to the kth power, or I guess I should say log to the kth power n. This is polylogarithmic. So this would be stuff like log square n, log cube n, log 4n, and so forth. We have O of n. This is considered linear time. We have O of n log n. There really isn't a name to go with it. We just say n log n, so it's just n times log of n. We have O of n squared. We call this sometimes quadratic time. A lot of times I'm probably just going to say O of n squared. We have O of n cubed. So this is also known as cubic running time. So it takes a cubic number of steps, n cubed number of steps. We have O of nk, where k is just some constant. So I mean, it could be 2, 3, 4, 5, 6.3, but this is a polynomial running time. And then finally, we have O of 2 power n, and this is considered exponential time. And notice that I ordered these from the fastest to the slowest. So constant time is the best that we're ever going to get for an operation or an algorithm. Exponential is the absolute worst. In fact, if you have an exponential running time algorithm, it's a really bad algorithm. We also have a couple of rules that we need to mention. These rules will come in very handy whenever we're analyzing the algorithms where different sections may have different running times. So the first rule says that let's say we have two different running times. We're going to call one t of 1n and the other one t2 of n. So here we're going to say that t1 of n takes O of fn time and t2 of n takes O of g of n time. So what we say here is if we add the two running times, so t1n and t of 2n, well, that's just going to be the O of the sum of f of n and g of n. So we're just simply adding f of n and g of n together, and that would be the running time of adding these two running times together. Likewise, if we multiply these two running times, then in our O notation, it's just going to be the functions multiplied. So t1 of n times t2 of n is just simply going to be O of f of n times g of n. Now, the second rule is if t of n is a polynomial of degree k, then that means that t of n is going to be theta of n power k. So this means that we have a very tight bound. So if t of n is a polynomial of some degree k, so it could be like n cubed plus n plus 5, something like that, then t of n is going to be theta of n cubed in that particular example. So we know it's bounded above and bounded below by that n power k. And then our third rule, and this is an interesting rule actually, where log power kn is O of n for any constant k. So let me repeat that. Regardless of whatever value of k is, it can be 1,000. Log kn is O of n. And what this tells us is that logarithms grow very slowly. So we can say that the upper bound of this is always going to be linear time. Whenever we actually use the big O notation, or technically any other notation for that matter, we ignore the constants and low order terms. I already mentioned a little bit about the constants, but we also ignore low order terms as well. And you might think, why? Shouldn't those be included to get a more accurate running time? Well, yes and no. We could add them, but it actually makes the running times more complex because the reason behind this is whenever n is sufficiently large, I'm talking like billions and billions and billions, the constants and the low order terms don't really have a factor in how long the algorithm is going to take. So let me give you a couple of examples. Let's say we have O of 2n squared. The 2 is not needed. We can just say O of n squared. If n is like 4 quadrillion, it really doesn't matter whether we have the 2 in there or not, as far as how large this is going to take with respect to the size of n. So we can just ignore the constant factor here. In another example, if I have something like O of n squared plus n, technically that's more accurate, but we can just say O of n squared because n squared is the dominating term. So since n is the low order term, we can just take it out. Yes, it's there, but whenever we're analyzing the algorithm, we can just look at the dominating term if we're adding several things together. The last thing I'm going to mention is that whenever we're analyzing an algorithm, we have to have some form of model of computation. Think of this model as a set of assumptions that we make whenever we execute a program. So we look at how the instructions are executed, how long some of these instructions take, but we have to have some set of assumptions ahead of time, and we put this set of assumptions together and we call it our model of computation. So our model is that the instructions are going to be executed sequentially. So if I have an algorithm, I can run one instruction at a time. We can't do them in parallel. We can't do it in some other weird order. It's just they're done sequentially. And then we'll say that simple instructions such as addition, multiplication, comparison, subtraction, division, assignment, and so forth, all those very basic instructions would take constant time. And we're not worried about exactly how much time it takes. We're just going to say that each of these simple instructions take a single step of the algorithm. We know that the actual execution times are going to vary by instruction. The time it takes to do addition is going to be faster than the time it takes to do multiplication, for example. Well, actually, that may not be true, depending on what you're multiplying by. If you do it by a power of 2, there's actually a faster way. But the point is, we know that the actual execution times for these instructions are going to be different. But from an algorithm perspective, when we're analyzing it, we're just going to assume that they all take constant time.